All right, so we're going to take a look at, this week is basically, in one day, we're going to look at the idea of what a sine or cosine function looks like if you graph it. All right, so basically a graph of it looks like, I can show you, it looks like that. Okay, it's a wave pattern. And there's four basic things we can do to that wave to change it. We can take and compress it like that, or we can stretch it. That's considered the same thing, stretching or compressing horizontally. I can also stretch or compress it vertically. Okay, that's compressing, that's stretching. Okay, that's the second thing we can do. Third thing we can do is move it to the left or move it to the right. And the fourth thing we can do is move it up and move it down. I can't show you that on here, but you can imagine just moving it up, moving it down. All right, so those are the four things you can do to a graph. The only one that we're going to look at is moving it left or right. Okay, we'll look at that one. We're not going to look at moving it up and down. We're not going to look at stretching it up and down. We're not going to look at stretching it left and right. Right. And when we move it left and right, okay, the name for that is called a phase shift. Right. So again, the only transformation we're going to study is a phase shift. We're not going to do the other three. These are what the basic functions look like that we're graphing this week. Okay? Sine and cosine. If I graph both of those at the same time, you'd see they look pretty similar. Okay, here's your, you don't need a graphing calculator, just watch me do this. Okay, the first one you're seeing come up is going to be sine. Okay, that's in blue. Second one that comes up in red is cosine. Basically, they're the same thing. Just imagine taking the red one and sliding it to the right, or take the blue one and slide it to the left a little bit, and they'd line up perfect. Okay, but they're both a wave. That's the point. And these functions are called periodic functions. Okay, the reason they're called periodic functions is because they repeat themselves. Okay, and I'm going to show you that in a picture. Okay, but there's a certain amount of distance they have to go through on the screen before they start repeating. Let me take, let's get rid of cosine. Okay, let's look at the graph of just sine. And let's take that and look at that. Okay, so there's your graph of sine. Okay, let's just focus on, move it over. Let's just focus on that part. So it starts right there. And if you kind of trace it along, it goes up, it goes down, it comes back up, and then after that dot, it would repeat the same pattern you've seen right here. Okay. That basic pattern is going to be repeated over and over. Right. So if you wanted to continue the graph, you just put another copy of it there, and you could just keep doing that. Right. That pattern just repeats. Okay. This section has a special name. Okay. This is called one. I think I have it next. One period of the function. Okay, a period is basically the amount of distance it has to go through before it repeats itself. Okay, so on this particular graph, that's from this green dot to that green dot. That's the amount of distance it has to go through before it will start to repeat itself. And the name of that is called a period. So from here to here, this is one period. Okay, between those green lines. right, so let's say I were to graph this. Let's go 0 to let's go 3 pi over 2. Is that picture a full period? Nope, not quite. Okay, to be a full period, you'd have to see a little bit more. It has to come back up and end where it started. Okay, this is 3/4 of a period. Okay, if I did this, let's say I just went here. Now what you're looking at is half a period. Okay, you're just looking at this top half. It never dips below the x-axis. That's only half a period. Okay. Full period looks just like that. Goes 0, goes hit up, comes down, and then it's going to end right where it started. That's one full period. Okay, any questions on that? All right. So as I was changing that window, sometimes I showed you part of a period, full period. If I want to show you one full period, it's that wide. Okay, that's how wide the period of sine and cosine is in radians. It's about 6.28 units wide. Does anybody remember what 2 pi is in degrees? Yep, 360. So if you were doing a graph in degrees, you'd have to show at least 360 degrees on the x-axis in order to see a full period. If you didn't show up to 360, it wouldn't look like a full period. Okay. And if you have a graphing calculator, if I put it in degrees, let me start at 0 and end at 360. Okay, if I start at 0 and end at 360, you should see exactly one period. What if I went from 0 to 720? What would you see there? Tyler? Yeah, you'd see 2 full periods. There's 0 to 360, and now there's 360 to 720. That's 2 periods. What if I did 0 to 180? I would only see half a period. You're going to see the top half. It's never going to come back down. Okay. So if you want to see a full period, whether it's sine or cosine, you have to go at least 0 to 360. Anything more than that, you're going to show more than one period. Right, so when we want to graph a trig function, it's helpful to have 5 points. You like to know where it starts, where it stops, the highest, the lowest, and what's right in the middle. If you've got those 5 points, I think that's enough to make a picture. If you have less than that, it's kind of hard. Okay, so I call these the 5 key points, or the 5 important points when you're trying to graph a trig function. Right, now the directions here say to graph transformations. We're only studying one transformation, and that's phase shift. Okay? So if we want to know where something is going to move to, okay, if it's going to move left or if it's going to move right or up or down or whatever, we have to know where it started at. Okay? It's like if I said to you, drive 2 miles north, that's where I'll be. North of what? You have to know north from what, where are you starting at, and then where are you moving to. Okay? So anytime you want to graph a transformation, you have to know where the original graph starts. Okay? Those are the graphs I've been showing you on this screen. And this table shows you where the graph starts for sine. Okay? Those are the 5 important points you need to know in order to graph sine. Okay, let me put up the graph at the same time. right, so let's look at the table and see how it matches up with the graph. When you're at 0, when x is 0, y is 0. Okay? Sine goes right through the origin. The next point is pi over 2. If you wanted to know in degrees, that's 90 degrees. If I go to pi over 2 on this graph, just type it in. It's kind of hard to see, but pi over 2 is where the cursor is at its highest value. Okay? It's blinking. And the highest value it ever hits is 1. When I get halfway through the period, that's at pi, and I'm back at 0. 3 pi over 2, that's 270 degrees. Okay? When I get to 270, I'm 3/4 of the way through my period. I'll show you that one. And that's the lowest value that I ever hit, -1. And then when I get to 2 pi, I'm back where I started. Oops, 2 pi. Let me just type it in this way. It's about 6.28, 6.27. It's actually off the edge of the screen. But when we get back here, we're back at 0. Okay. So any questions on that? That's where the sine function starts. If you don't move it at all, those are always your values. Okay. And let's look at cosine. Cosine and sine are they're very similar. Okay, but notice when x is 0, it's not going through the origin. When x is 0, what does it look like y is? Y is up at what? 1, yeah. Okay, so when x is 0, y is up at 1. I'll just cover that for a second, then I'll get rid of it. How about when we're at pi over 2? What does it look like our y value's at there? Yep, we're at 0. Okay. How about when we're halfway through at pi? Yep, we're at -1. And then 3/4 of the way through, 3 pi over 2. What's my y value there? We're back at 0. And then how about at the very end when we hit 2 pi?
1.
We're back at 1. So it's the same y values, but they're in a little different order. It's all 1s and 0s and -1s. So that's your graph of cosine. Any questions on that? And the reason we need these tables is because what we're going to do, the only transformation we're going to do, is we're going to take this graph and push it left or push it right. But we have to know where it starts in order to figure out where it's going to go. Okay, this is where it starts. All right. All right, so after we have the original tables, then we'll figure out, after we move it left or we move it right, what are the new points? Okay, these are the originals. We have to figure out where these points are going to move to. All right, so now let's look at the one transformation we're going to do, which is a phase shift. Okay, so just a little background about sine and cosine. Now I'll show you what a phase shift is. Okay, phase shift is when you move the graph left or right. Just like this. That's a phase shift. That's a small phase shift. Okay, if we did a bigger phase shift, that's a much bigger phase shift. And notice what happens if we shift it 360 degrees. We've shifted it so much, we've ended up back where we started. You can't tell the difference between shifting it 360 and shifting it 0. It's the same thing. Okay, that's a phase shift. And as an equation, that's what a phase shift looks like. It's when you take the original function, could be sine or cosine, depends, we'll do one of each, and you add or subtract a number to the x value, okay, inside the parentheses. Okay, so here's an example of a phase shift. Sine of x plus pi. If you were going to do it in degrees, that would say x plus 180. It's a 180 degree phase shift. Y equals cosine x minus pi over 2. That's another phase shift. Pi over 2 is 90 degrees. Right, so if you did this in degrees, it would say x minus 90. What do you think the difference is going to be whether we use a plus or a minus? What way it goes. It's either going to shift left or it's going to shift right. One of these is left, one of them is right. Okay? And you can shift by any amount you want. Okay? Notice in this program, if I want to shift by 25.56 degrees, I can. Okay? Generally, the shifts that we're going to do are common ones. We're going to do a 45 degree. We're going to do 90, which I can't quite get, but we're going to do a 90 degree shift, and 180. Okay? We could do others, but those are the common ones, 45, 90, and 180. Okay? So in radians, you'll see pi over 2, pi, and pi over 4. All right, so there's basically two rules when you have a phase shift. You just have to figure out, does it move left or does it move right? If you subtract, it moves right. Okay, and that doesn't really make common sense. Because you think of like a number line, think of where the negatives are on a number line. The negatives are to the left. So you would think common sense, if you have a negative, you would go left, but phase shift doesn't work that way. So if you subtract, you shift right. How much do you shift right? It depends on how much you subtract. The more you subtract, the more you shift. So if subtracting is going to shift you right, what do you think adding is going to do? That's going to shift you left. Okay, and that's really all you need to know. Okay, subtract, shift right. Add, shift left. That's how you could summarize that whole thing. So it's almost like the opposite of what common sense would tell you. Okay, I'd like to think when I add, I think add on a number line, add is to the right, but it doesn't work that way. So keep that in mind, that we're doing the opposite of what you would expect. All right, so last thing before we look at an example is how do we figure out what those new points are going to be? Okay, how many key points are there? There's 5. We're going to shift them left or right. When you shift something left and right, what axis is it moving on, the X or the Y? Yeah. So if I shift left and right, all I'm doing is sliding something left and right. Okay, it's not up and down. So what values here are not changing at all? The Y values. Focus on the height of that point. Okay? The height of it is not changing. It's just moving left and right. So because the heights aren't changing, we're going to copy the Y values from our original tables. Those are not going to change for any problem we do today. If we do a sine problem, these are going to be your Y values. If we do a cosine problem, those are your Y values. You're never changing those numbers. Now, if we move something up and down, then they would change, but we're not doing up and down. So if the Y's are going to stay the same, then that means what ones are going to change? The X's are going to change. Right, so to figure out what our x's are going to be. Let's keep these two rules in mind. Look at what's been added or subtracted. Let me show you an example. In this example, that says minus pi over 2. I've subtracted pi over 2. Any questions on that? Just what the example says, minus pi over 2. So once I figure out what's been added or subtracted, I do the opposite. Why? Because we just talked about that with phase shift. It's the opposite of what you would think. Okay, I'm going to do the opposite of minus pi over 2, which would be plus. I'm going to plus pi over 2. What am I going to plus pi over 2? I'm going to plus it to all the original x's in that table. I'm going to add that number to all of them. Right, and we'll go through two examples of a phase shift. And those are going to be the only examples that we graph today. Okay, so what I've done is I copied the original table for sine. That was back a couple slides. I just copied this table. So we'd have it for example 1. All right, so now let's make a new table. All right, so normally the first thing you have to do to look at it is say, what transformation is this? Okay, there's 4. There's a phase shift. That's what we're studying. There's a vertical shift. There's an amplitude change and a period change. Okay. The way I know this is a phase shift is I've added or subtracted inside parentheses. Okay. And it's the only one we've studied, so of course it's the one I'm going to ask you about. All right, so now, because we're studying a phase shift, what values did I say never change when we do phase shift? The y's. Okay. The y's stay the same. Copy them down from your original table. 0, 1, 0, -1, 0. Okay. Any questions on that? Now my x's, okay, I'll put those down. Just write them off to the side a little bit. These are the originals. Pi over 2. Pi, 3 pi over 2, and 2 pi. Now I'm going to do something to all of these. I have to find my new x's. Okay. Anyone think they can tell me what I'm going to do to all my old x's to get my new x's? And the directions are basically step 2. Yep.
So put the pi over 2 to every single x value.
All right, let's go through it step by step. Determine what has been added or subtracted. Did we add or subtract here?
Subtract.
Yep, subtract pi over 2. And then it says do the opposite of that to each of the original x's. So you said we subtracted pi over 2.
And then you add.
You added. Okay, I know it's weird, you got to do the opposite, but that's just the way a phase shift works. Okay, without getting into a 20-minute discussion why. Okay, just do the opposite. So I'm going to add pi over 2 to every one of those values. And we'll put our answers right in that box. All right, first one's not too bad. What's 0 plus pi over 2? This is pi over 2. Okay. Next one, also not bad because it already has a common denominator. What's 1 pi over 2 plus 1 pi over 2? Again? 2 pi over 2. Ah. 1 pi over 2 plus another 1 pi over 2 is a 2 pi over 2. Now, in this case, it can reduce. What does 2 pi divided by 2 reduce to? 1 pi. Yeah. Just 1 pi, or you could just put pi. All right, now the next one, okay? It says pi plus pi over 2. I just need to add those up, but I got to be careful because think about what you know about adding fractions and denominators.
Are we just taking the next x value? Like,
Yeah, basically that's what happens. Yep.
So this one would be 3 pi over 2.
Yep. It's going to end up being 3 pi over 2, but I'm just going to show people that. Yep. But it will be 3 pi over 2. Very good. All right. So we're going to take pi, and we're going to add pi over 2. If I don't have a denominator, what can I always put right there?
1.
A 1. Now, since the denominators are different, can I add those together? No, you'd have to make them the same first, if you didn't notice a pattern. What's the common denominator between 1 and 2? 2. What do you multiply 1 by to make it what you guys just said? If you do it in the bottom, you got to do it in the top. What's 2 pi over 2 plus 1 pi over 2? There's your 3 pi over 2. If you're confused, think of it as 2 over 2 plus 1 over 2. That would be 3 over 2. The only difference is we have a pi in the top as well. So it's 3 pi over 2. All right. Let's do the next one. 3 pi over 2 plus 1 pi over 2 gives me 4 pi over 2. Now, can I reduce it? Yep, to 2 pi. And the last one, 2 pi plus pi over 2. Okay, my common denominator would be 2. It's usually 2 in these kind of problems. So double the bottom, double the top. 4 pi over 2 plus 1 pi over 2. 5 pi over 2. And that's our table. If you hadn't reduced it, okay, I want you to reduce it. Like 4 pi over 2, I want you to reduce it to 2 pi. But watch what happens if you don't reduce it. 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. What do you think the next one would be?
6 pi.
6 pi over 2, 7 pi over 2, 8 pi over 2. Okay, but we stop here. Okay, so when you do this, sometimes you see a nice pattern. And if you see the pattern, you don't have to keep finding the common denominator. Just go with the pattern. If you don't see a pattern, do what I just did here. Okay, any question on that? So on a test, what I usually do is I make each one of these worth 1 point each. So 5 points if you get the y's, 5 points for getting the x's. And then the picture, which we're about to do, I make that worth 1 or 2 points. Because once you have the table, the picture is easy. All right, let's make a picture. Easiest way to make your picture is label your x-axis with the values you have up above. Don't label it 1, 2, 3, 4, 5, 6, because we don't have nice numbers. Okay? Use the numbers you have. You can use any numbers you want as long as they're evenly spaced. Okay? And these are evenly spaced. I think in degrees you'd see that easier. It's 90, 180, 270, 360, 450. It's every 90 degrees. Okay. We're just doing it in radians, so it looks a little different. Pi, 3 pi over 2, 2 pi, 5 pi over 2. What's the highest I need to go on my y-axis?
1.
1. And the lowest? That's going to be the same for every single problem. 1 and negative 1, always. And now just graph your points. Pi over 2, 0. Pi, we're at 1. 3 pi over 2, back to 0. Negative 1, back to 0. Now when I connect those dots, remember the pictures I showed you? They were all kind of smooth curves. Okay, nothing here is like a sharp point. Okay, everything should be nice and curved. Just like that. Okay, and that's a phase shift. if I wanted to sketch the original, this is where the original would be. Right about like that. Okay, you don't have to sketch the original right now. I'm just showing it to you. That's the original. That's the new one, the shifted one. Any question on that? Okay, that's the hardest thing we're doing today. All right, we'll try one more phase shift, and then we'll finish up with a couple things that are non-graphing, just a calculation you have to do. All right, cosine of x plus pi. First, can somebody tell me how I know that that's a phase shift? Because we've added, and where did we add? In the parentheses. That's the whole key. If you ever had a problem like this, that's a totally different problem. We're not studying this one. That would be a vertical shift. This is a horizontal shift. All right. So Tyler just told us it's a phase shift, so we're going to move left and right. So somebody remind me, what column stays the same? The y's. When you move left and right, you're not changing anything on the y's. Adam, do you remember what my y's are for the cosine?
1, 0, -1, 0,
1, 0, -1, 0. Perfect. If I was grading this, you'd get 5 points for those 5 right there. All right. Just for reference, I'm going to drop my pen. I'm going to put down the original x values. 0, pi over 2, pi, 3 pi over 2, and 2 pi. If you like to think in degrees, it's 0, 90, 180, 270, 360. Am I going to add or subtract this time? I am. I'm going to subtract. What am I going to subtract from each one? Pi. That's it. Okay, and then we'll just put our answers in that table and make our sketch. Okay, 0 minus pi. How much is that? Negative pi. Let's do this one. What's pi minus pi?
0.
I just did that because it was quick. What's 2 pi take away 1 pi?
Pi.
Just pi. Okay, now we're going to do the other two. Pi over 2. Take away pi over 1. Common denominator would be 2. So it's 1 pi over 2. Take away 2 pi over 2. Yeah, negative pi over 2. We've got one more to do. 3 pi over 2. Take away, common denominator again is 2. What's 3 pi over 2? Take away 2 pi over 2. 1 pi over 2. And that's our table. If you didn't reduce it, your pattern would be negative 2 pi over 2, negative 1 pi over 2, 0 pi over 2, 1 pi over 2, 2 pi over 2, 3 pi over 2, 4 pi over 2, 5 pi over 2. If you kept going. Okay. Any question on that one? Okay, let's make our graph. Okay, highest and lowest value on the y-axis is 1. 1 and negative 1. This time I need to label on the negative part, so we'll start with negative pi. Just kind of squeeze it in, negative pi over 2. Okay, 0 you don't need to label because that's the axis. Pi over 2 and pi. And just fill in your points. So negative pi, 1, negative pi over 2, 0, 0, negative 1, pi over 2, 0, pi 1. Okay, this is the graph some people make a mistake with. They end up sketching it like that. But remember, it looks kind of like a V shape, but that's just because it's, let me line these up. It's the middle part of one of those sine waves. Okay, so try to give a little curve to that V shape. Just don't draw it like a point. So that something like that is fine. Okay, so any question on that? Okay, so that's definitely something you want to know for the final, how to shift the graph left and right. Okay, last two things we're going to look at are just a calculation. It's nothing we're going to graph. Okay. How many transformations are there altogether? We're not learning them all. We only learned one. But there are 4. Okay, you did shifting left and right. We're not going to do the other 3. All right, let's get this. Okay, the height of these graphs that you draw, okay, how high they go, that's called the amplitude. Okay, so here's just a picture of a sine wave. What I've marked right there, that's called the amplitude. It's how high the graph goes. Kind of measure the distance from the center of it. Okay. Okay, so although we're not going to graph amplitude changes, I'm going to show you what an amplitude change looks like. Okay, so with a phase shift, that's when you added a number to x in the parentheses. Well, with an amplitude change, that's when you stick a number in front. There's an example of an amplitude change. 3 sine x. Negative 2 cosine x. 1/2 sine x. Those are all examples of amplitude changes because we have a number in front. Okay, and what do you think the difference would be if I graph, let's graph sine x versus 3 sine x? Okay, we're going to change the amplitude. What do you think that 3 is going to do? You think it's going to make it taller, or is it going to make it shorter? You think it's going to make it shorter? Taller? Yeah, it's going to make it taller. How many times taller do you think it'll make it? It's going to make it 3 times taller. And I'll just show you how that looks. Okay, here's your original. And here's what happens if you put a 3 in front. It's like you just took and stretched it out vertically. So before the highest was 1 and the lowest was negative 1, what do you think the highest is now? 3. And the lowest? Yeah, negative 3. So the only thing that I want you to know how to do with amplitude, you don't have to know how to sketch it. I just want you to know if I give you an equation, how can you look at it without drawing a picture and tell me what's the amplitude? How tall is it? Yep, the only thing you have to do is look at the number in front and take the absolute value of it. This negative on the 2, the negative does cause something to happen, but it would only be seen if you draw a picture. Okay, it does not affect the amplitude, whether the negative is there or it's not there. Okay, take the absolute value of the number in front, and that's the amplitude of your picture. Okay, let's try that. So in the graph, 3 sine x, what's my amplitude? 3. How about negative 2 cosine x? 2. And how about somebody else tell me what's the amplitude in 1/2 sine x? 1/2, or 0.5. Yeah. What if I change the original problem to that? What's the amplitude now? It's still 1/2. Okay? Remember, it's absolute value. Okay, so that negative disappears. Okay, the negative would have an effect if we drew a picture, but it has no effect on the answer to this question. What if I put a negative in front of the 3? What would the amplitude be then? Still 3. Yeah. What if I gave you one like this? Let's do... What's the amplitude there? What is it? 8. It's still 8. This plus pi has nothing to do with that amplitude at all. What is the plus pi? It's what kind of transformation is it? That's a phase shift. Yep. Okay. You can shift left and right all you want. It's not going to change the height. That's the only thing you have to look at if you're changing the amplitude. Okay. All right, we try a few more. What's the amplitude of 3 sine x? Negative 4 cosine x? 4. 1/2 or 0.5 sine x? 0.5. How about negative 0.25 cosine x? 0.25. Okay, just the absolute value of the number in front. All right, so any questions on how to find the amplitude of a function? And these technically I could write y equals. That's how I should technically have it. All right, so that's the first thing we're going to do that's not graphing based, just simple calculation. And the last thing. Okay, so I just showed you guys how to figure out the amplitude. I didn't show you how to sketch it, and we're not going to learn how to sketch. All I want you to do is identify amplitude. The last thing I'm going to show you is how to identify a period. Okay? The period is the distance between, say, that point and that point. Okay? If you measure the distance between them, that tells you the length of one period. Just pick any 2 points that correspond. You could pick this one and this one. You could pick that one and that one. Okay? It would come out the same. Now, if I go like this, what did I just do to the period? I squished it, I compressed it. How about if I did something like that? What did I do to the period now? I lengthened it. Okay? So the last thing I'm going to do is I'm going to give you equations just like this, and I'm going to ask you to find the period. Okay? It might stretch out, it might compress. Does anybody remember what the period is if we don't change it? How many degrees you got to go through before it repeats itself? 360 or 2 pi. That's the normal period. If you never change it, you don't do anything to it, it's always 360 degrees. Okay, so this is what period change looks like. We're not adding or subtracting a number inside parentheses. That was a phase shift. We're not sticking a number in front. That would affect the amplitude. We're sticking a number inside next to x, and we're multiplying. Okay, so this is the last thing we're going to look at. Okay, and we're not going to do any sketching. I'm going to just give you an equation, and basically I'm going to ask you to find the period. Okay, in your book, they use the letter T for period. I don't know why they don't use P for period, okay, but I did it the way your book does. And this is how you find the period of a function. You take 2 pi, which is the original. Okay, that's the period if you never change it. And you divide by b. Well, what's b? B is the number that you stick in front of x. Okay, so if you're going to make a reference sheet for your final, that's a formula you definitely want on it. There's one question on there that says find the period of the following. And that's how you do it. Take 2 pi and divide by the number in front of x, which we call b. Call it whatever you want. Right, so we'll just try 3 examples of that, and then that'll be it. Okay, so the first one says find the period of y equals sine 2x. Now, sometimes when I ask people to find the period, they say, oh, it's 2. When I say, no, 2 is just what? That's just the... It's what?
It's B.
It's b. 2 is just b. So once you know what b is, that's good, but now fill it into that formula. So it's going to be 2 pi divided by, what's b?
2.
2. So what's the period of this? Pi. Is that shorter or is that longer than the original? Think back, what's the original again? 360 or 2 pi. So is that smaller than 2 pi or bigger? Smaller. Period got shorter. Okay, let's try this one. To find the period of cosine 5x, what number goes on top? 2 pi. That never changes. What goes on the bottom? 5. That's my period. That's quite a bit shorter than 2 pi. In fact, it's 5 times shorter. You took 2 pi and you divided it by 5. So it got a lot smaller. Okay? That would be like compressing. Okay? And the last one. Okay, what number goes on top? 2 pi. If you don't mind this time, I'm just going to write it as a fraction. I'm going to write it as 2 pi over 1. And what goes in the bottom? 1/4. All right, how do I do that? I have a fraction divided by a fraction. So yeah, I heard somebody say keep the top the same and then multiply by what? 4. You take what's in the bottom and you flip it. What's 2 pi over 1 times 4 over 1? 8 pi over 1 or just 8 pi? Is that longer or shorter than 2 pi? Longer. In fact, it's 4 times longer. Right? So that would correspond to a graph that's stretched out. Does anybody know what that would sound like in terms of... yeah, let's look at it. So, did I play an amplitude change for you?
Yeah, I think you did. Yeah, he did. No, you did.
I did?
I swear to God.
I did the amplitude change?
No. Well, maybe you mentioned.
I mean,
I don't know.
I played those sound? I don't think I played that. So, if we do an amplitude change, okay, let's go like that and play it. What happened to the sound versus this? It got what?
Quiet.
Yeah, I got the volume changed. Okay. So in terms of a sound, if you change the amplitude, you change the volume. So what do you think is going to happen if I stretch or compress the other way? What do you think that would sound like?
It's going to be a high pitch and it's going to go low pitch.
Yeah, it would change the pitch. So we can go from something that's a pretty low pitch. Let's try that. Okay, to something, let's not do that. Let's try maybe moderately high pitched. I'll turn it up a little bit. It's a little higher pitched. Okay, now we get up around 9,000 hertz. Okay, that's basically how much we've compressed the period. It's like compressed 9,000 times. It's a little higher pitch. Okay, a little higher. At some point, okay, I can't really hear that one anymore. And then up at 20,000, a lot of people can't hear that one either. So the effect on the frequency is the effect of stretching and compressing changes the frequency. And we can do all kinds of neat stuff with that. Like if I know the frequencies that you press on your cell phone, which I do, I can generate certain sounds. Like if I can type in, I'll show you something. Type in 1209 and 770. But they have to be separate. Okay, so what I'm doing now, you can see the picture. It's two different frequencies played at the same time. And this is going to sound just like I'm pressing a button on your phone. It sounds like you're pressing the number 1. And if your phone was on, okay, and let's say you were in a menu that said press 1 to check your voicemail, and I did this, it would then go in and check the voicemail. It would think you pressed the button for a 1, even though it just heard the frequency. So you can control a cell phone with it. Changing frequencies, the military has applications for that. There's a device called an LRAD. It's called a long-range acoustic device. And it plays two frequencies or multiple frequencies that are very annoying to hear. So if you're standing where they're playing this sound, you don't want to be there. You want to move away. And it's so powerful, if you stay there, it can cause deafness, permanent deafness. So it's a non-violent weapon just with sound to kind of get people to move away. And they've used it on different TV shows. There's some examples of how they used it. Sometimes cruise ships have them, because cruise ships, if they're ever attacked, they can't really, they're not like an army or a navy vessel. They can't put missiles on cruise ships. But they can put an LRAD so that if a boat was coming at them, they can aim it and hopefully that boat decides to go in a different direction. If not, then, well, there's a problem. Yeah, there's all kinds of cool things you can do with sound frequencies. Okay, but we're not going to really look at too many of them. If people want me to do the cell phone thing after, I can show you. If not, you can work on some problems I got for you. All right, so the homework, I don't think it's going to take you too long. It's a worksheet. It's graphing 5 phase shifts. Okay, I'm going to pass that out. And then it's also answering these 4 questions. I want you to tell me the amplitude of each one and tell me the period of each one.
So we're bringing that to you next, right?
Yeah, I'll see you next academic week. Yep. So this won't be due until
Oh yeah, your calendar.
April 4th. So April 4th.